Hello students, in this lecture we'll be looking deeper into layout design. We'll be using a software called Microwind for our layout design. This software, like DSCH2, is an open source software and is a portable software. I have already given you a link to this software. You have to just download this software, and after you download you will get a folder like this. Now you have to search Microwind. You cannot search from here because it will create errors similar to the case of DSCH. You just have to look for Microwind here. I can find here we have Microwind. So let's just switch on Microwind, and I need something to draw to, so I'll be using Autodesk. So this is a layout of Microwind. This black screen over here, what we find, this is a p-type substrate. That is, the black screen is a substrate which is of p-type. Now, as you can see from this bar, it is almost similar to what we had in DSCH, and this software and DSCH are virtually very similar. Now, at first we want to draw an inverter over here. We want to make an inverter. So in order to make an inverter, the circuit is like the following. Connected with the VCC, we have a PMOS, and with that we have an NMOS, and it is connected to ground. PMOS and NMOS are internally shorted. Here we have input, here we have output. Now we can see that this is the source of PMOS, this is drain, and this is the drain of NMOS, this is the source. So this is a basic inverter that we will be making. In order to make the inverter, what we need we need a PMOS and an NMOS. So we have already known that PMOS is made with p-type diffusion layer. In case of PMOS, there are two p-type diffusion layers separated by a polysilicon gate. So we here in the palette we take p plus diffusion, and we click that and we drag to make a rectangle. So this rectangle is a p-type diffusion layer. I have drawn one, but we know in case of PMOS there are two p-type diffusion layers. So what do we do? What can we do? We can create the gate in the middle. The gate is made up of, as we have stated in theory, the gate in the earlier stages they were made up of metals. Now they are made of polysilicon, but the metal gates are coming back. So in case we will be using this polysilicon, if we draw this polysilicon over the gate, over the p-type substrate, what happens is this polysilicon divides the substrate into two parts, this part and this part. This part is called either drain and source. This part is also either drain and source. So now we have two diffusion layers separated by a gate. So this is our PMOS. One thing is still missing from this PMOS, that is N-well, because this is a p-type substrate, and for PMOS we need an n-type substrate. So make the substrate n-type. We surround the whole PMOS with N-well. So this is our PMOS. Similarly, we want to make an NMOS. We can zoom out by pressing here. So we want to make an NMOS. In order to make NMOS, we need N plus diffusion layer. We can see it here. N plus diffusion layer. And again, since we need two diffusion layer, we can separate it by polysilicon. Here we have separated it by polysilicon. Now we have an NMOS. So we have already developed a PMOS. We have already developed an NMOS. Now if you look into the circuits, the gate of PMOS is connected to the gate of NMOS. Here this is the gate of PMOS and this is the gate of NMOS. It is to be noted that in case of NMOS, there is no need of creating any well because the substrate itself is a p-type substrate. Now this is a polysilicon, this is a polysilicon which will be connected in the circuit, as we can see in this figure. So if we want to connect it, we can connect these two with lot of different things, but very easy and efficient way to connect it would be using polysilicon. Why would that be? Because this is also polysilicon, this is also polysilicon. So we can connect it using polysilicon. This gets connected. Now let us assume that we do not connect it with polysilicon. If you want to connect it with metal, then what would happen? Let's see. We draw a metal here. So this gate and this gate should be connected by now. But see what happens. Here you can see a saw sign, and with that we can create 2D vertical cross section. We click this and we drag it from the middle and we see the cross section. We can see this is our polysilicon, this is our polysilicon, and this is our metal. They are not internally connected. In order to connect them internally, what we need to do, we need to put contacts. So creating contacts will increase the fabrication difficulties and weight of the actual inverter. As a result, we want to minimize the use of contacts as much as we can, and so we will not be connecting this with metal. We will be connecting this with polysilicon, so that we do not need any external contacts. It is to be noted that it can be connected with metal and the effect will be same. There is no problem with it. Now we have the gate connected. Now we have to connect the drain of the PMOS with the drain of the NMOS. Now MOSFET is a symmetric device. That is, if this is a PMOS, we can consider this is source, this is drain, or we can consider this is drain, this is source. It's just up to us. So let us assume that this over here is the drain of PMOS, and again this over here is the drain of NMOS. So we will have to connect drain of PMOS to the drain of NMOS. Now one thing is to be noted that this is a p-type P plus diffusion layer. This is an N plus diffusion layer. So these two are two different things. So they cannot be connected with the same thing. So that is, we cannot connect them by either p-type or n-type diffusion layer. So what we are using is, we are using a metal. Now metal is different and diffusion layer is different. As a result, here we need to have a contact that connects the metal with the diffusion layer. Here too we need to have a contact that connects metal with diffusion layer. In order to get this contact, we have some ready-made contacts available. We can see N is for N-type diffusion layer and metal 1 contact. This is metal 1. We have taken it from here. So if we say click N and if we bring it here, it connects the metal to N-type diffusion layer. Similarly, here P is a P plus diffusion layer and metal. If you click it and take it here, it connects the p-type diffusion layer with the metal. So we may require other complex metal, for example metal to polysilicon, polysilicon 1 to polysilicon 2 and other things. So here we have contact builder, it creates complex contact. If we click here, we can see we can create contacts from metal 5 to metal 6, metal 4 to metal 5, metal 3 to metal 4, or poly to metal, N plus diffusion. We can create different types of contacts here. We don't need it now. So one thing is to be noted, see there are metals like metal 1, metal 2, metal 3, different types of metal. Why do we need so many types of metal? Because see here we have this metal connection. Now if you want to make a different connection with metal, that will go like this and this will get shorted. As a result, it will give an erroneous result. So what we do, instead of doing this, we draw this with metal 2. As a result, this is a different layer, this is a different layer. They do not get mixed. We can see this by observing the cross section of it. See, in this case, metal is connected to here via it is connected to contact, it is connected to N plus. Here by contact it is connected to P plus, and M1 and M2 are not touching, that is they are isolated. But if in this case, if we had used M1, then what would have happened? Let us see the cross section again. See, M1 that would have been connected, because M1 is in this layer, so we cannot see this at this moment. So let us just connect it again. So our connection is almost done. We have our VCC, we have our PMOS, and we have connected it to NMOS. Now we need two rails called VCC and ground. So we take metal and we draw this metal layer which will act as a VCC, and here also we draw a metal layer which will act as our ground. Now VCC will be connected to the source of PMOS. So this VCC will be connected to the source of PMOS. We take a metal and we connect it to the source of PMOS. And again this ground will be connected to the source of NMOS. So again we take metal and we connect to the source of NMOS. Again we'll be needing contacts. We'll be needing contacts. So this side is P type, so we need P type contact. The bottom side is N type, so we need N type contacts. Now what we need to do again, we need to do is we need to connect. We can see here blue arrow, this is our VDD supply. We can connect VDD to this. This ground, we have ground supply, we can connect ground to this. Another thing is, this is our gate. In gate we input a clock signal. Here we have a clock. We can add a clock and connect it to this. When we click this, this dialog box will appear. High level 1.2 volt, low level 0 volt. This high level 1.2 volt has to be same as this VDD. It is very important. This high level needs to be same as the VDD. That is number one. Second, low level will be 0. So okay. And time low, rise time, time high, rise time. This actually indicates the clock frequency. So we can modify the clock frequency any way we like. At this moment we do not require this. Another thing is to be noted, this is visible in CMU, this option. If this option is written visible in CMU, then when you simulate it to check whether your layout is right, that will be visible. That will be, this wave shape will be visible. If you click this not in CMU, it becomes not in CMU and that will not be visible in the output. So in order to check the output, we need both input and output side by side. So we will keep it visible in CMU and we'll press assign. So clock input has been assigned. Now we want to see the output. So in order to see the output, there is a visible node or I over here. We click it and the output will be connection between the NMOS and PMOS. So we put the output here. Sorry. So after we put the output here, we can name it anything. I'm not changing the name, and we have to see there is visible in CMU written here or not, and we assign this. Another thing is required. What it is required? See, this is a P-type diffusion layer connected to the VDD, and this is an N well. So as a result, since P layer is connected to VDD and there is a PN junction here, if there is a forward bias across the PN junction because the potential of P side is greater than the potential of N side. Because of this forward bias, what happens is there is leakage current and all sorts of current which will give us erroneous output. As a result, what we need to do, we need to make this N well. We need to make this N well connected to VDD as well. If we connect this N well connected to the VDD, this is actually called the N well. We are tying the N well to the VDD. If we do this, then we will not get any errors. So in order to do that, N well, we have to remember that N well is an N type of material. As a result, we need N type of contact. We click the N type of contact and we tie the N well with the VDD over here. Now almost everything seems alright. We have to check whether the design rules are fine or not, whether everything is okay or not. Let us give design rule checker. Nothing is, no dialog box is appearing or no problem, though no errors are being shown. So as a result, our simulation is, our layout is alright. Now, if we press this, we'll run the simulation and we'll see the output. Let's press this. For some reason, we cannot see the clock over here. Let's close it. This is not in CMU, that's why. If we say press it, visible in simulation and assign, then we run it. See, we have a clock here and we have output here. Now it is to be noted that okay, let's make it a little more clear. It is to be noted, see, when the input is high, that is clock is high, output is low. When the clock is low, output is high. So our inverter is working. So this is a basic inverter. Now let us let's see what happens if the design rules are not met. let us intentionally let me make some errors. For example, let this be the anvil. Okay. So we have tried to make some errors intentionally, and we press DRC. Then it shows error. The spacing between the metal is less than 4 lambda. If we remember, the two metals will, we have learned in theory that two metals will be at a distance of at least 4 lambda. In this case, the spacing is lower than 4 lambda, and that is being shown. So we have to increase this spacing. What can we do to increase this spacing? At first we can zoom out so that we can see a bit clearer. Then we click this, stretch and move. We click this and we click on this edge, the edge we want to move. We single click here, and this can move now. Now we are moving it here, and then we again run DRC check. After DRC check, we can see extra anvil surrounding diffusion P layer is less than 6 lambda. We have learned this in our theory as well, that this anvil from this P type substrate will have to be more than 6 lambda. So what we do, again we press this stretch button, we stretch it above to increase the distance here, we stretch it below to increase the distance here, we run DRC check again. Now there is no error being shown, and this is fine. Now if we simulate, we'll get our desired output. So we have learned basic layout design. In our next lecture, we'll be learning several other examples, and we'll get to learn the layout design a little more better. Thank you for now.